right, welcome everybody to tonight's Fort Worth Astronomical Society General Meeting. Next slide, please. All right, do we have any visitors tonight? All righty. You want to kind of, you get him with that, and I'll get this one. Raise your hand. Explain to us who you are and how'd you find us and what kind of telescope, if you have any.
My name's JC Kruger. I found you guys on Google, and you have a telescope. I haven't used it in a while, but I've been mostly just taking pictures right now with a camera and a tracking. No, not working. Okay. My name's JC Kruger. Found you guys on Google. I do have a 10-inch Dob, but I haven't used that in a while. I mostly just take pictures now. I'm just starting to get back into astrophotography. I used to do this a long, long time ago, so it's changed a lot since the last time I did this. So, as I'm learning, so equipment. Oh yeah, I just got a Canon camera and a 135mm lens that I've taken pictures and tracking with.
My name is Brad Blocker, and I heard about Fort Worth Astronomical by looking you up online years ago, and I finally just now, I might be a procrastinator. I'm just now getting here, and I've known about you guys for years. I keep thinking, I'm going to go. So I finally made it. My journey, I've always been interested. My brother got a telescope when we were kids, and so I was always fascinated with that. And then I picked up a used little Celestron, little Nexstar 4 SE, just a little one to play with. Then I saw this cool C-Star S30 Pro come out on some sort of thing, and I was like, well, that looks really cool. I didn't know you could do all that with one. So that's kind of where I'm at, and I'm wanting to learn more about it and just kind of figure it all out.
Well, welcome, Bill. Anybody else new? All right, next slide. New members. Brooklyn Watkins, did you come back or did we scare you away? All right. Susan Wagner. Heather Wilden. Clayton Swenson. No. And Douglas Brown. Yes, we scared them all away. Next slide. All right, quick information for the new people about FWAS. We're founded in 1949. We have about 334 individual members, 214 memberships in total, counting families and all that. We have a wide range of experience from beginners to professional. And if you want to learn something, you don't have a telescope, or you do and you don't know how to use it, we're here to help you out. Best way is just get hold of the club, come to one of our star parties, and one of our people can help you out, figure it out. And we're a nonprofit, so please feel free to make donations. You get a tax deduction for that. Next slide. All right. Our mission: to promote astronomy via public outreach, encourage and support groups interested in astronomy, cultivate observation and research among members, and we are working on this one to promote building of astronomy instruments. Make a club. We got a bunch of telescopes, so we are available for you to use. Next slide. All right, resources. We have a member's handbook. We got the Thompson Observatory, which is south here that we associate with. We have our own observing area with pads with electricity and Cat 6 cable, and we got a toilet out there. And over the next couple of months, we're looking to do some improvements out there. Hi, how you doing? And then, like I said, we got a bunch of telescopes that you can use, eyepieces, and then we have an online presence in our social media. Next slide. That's our observing area. We have an astronomical building. Astronomical building. This houses, we have 2 bunkhouses here. We've got a lot of equipment stacking in there right now. Here's our lease pads. They'll have electricity and Cat 6 cable going to them. Got a parking area. This is our compost toilet area. And then there's our maintenance building with all our other stuff to maintain the lawn out there. Next slide. This is just a list of the various types of telescopes and sizes that we have that you can actually use. They actually have an H alpha refractor that's here that you can borrow from. Raise your hand, where's Tom? Tom's got it. He's right there. Yeah. All right, next slide. These are our presence online. We have astro.com, Facebook, YouTube, Groups.io. That is our chat page where you can send messages back and forth and keep our files that everybody can get in. We also have Groups.io for APSIG, Astrophotography Special Interest Group. And then we have our merchandise store, Zazzle. You can buy all kinds of great stuff like this shirt. Next slide. You can find more information on our website, and you can join our club via NASA, or you can see Constantine, and he'll point you in the right direction to join the club. Next slide. All right, I'm going to hand it over to Big Bad Bill, introduce our guest speaker for tonight.
Thank you. So I'd like to introduce you to Dr. Joe Maciero. He is a solar system scientist. He was the deputy principal investigator for NEOWISE, Space Telescope NEOWISE, and he's going to be the science lead for the upcoming NEO surveyor. So please welcome.
Thank you very much. Really appreciate the chance to talk to you all. Sorry I can't be there in person. And I guess I'm a visitor tonight, so I heard about you when Bill invited me here. I have a 6-inch Dob at home. I had a 40-centimeter telescope, but that burned up in the Earth's atmosphere. We're working on building a 50-centimeter telescope. That's coming. I'll tell you about that at the end of the talk here. And I have shared access to a 200-inch telescope down in San Diego. That's pretty amazing to observe at. If you ever get a chance to come down to Palomar Mountain, highly recommend a visit because it is an absolute battleship of a telescope and one of the most beautiful pieces of engineering I've ever seen. But today I'm going to talk to you about our search for near-Earth objects. And so these are the asteroids and comets swirling around our solar system, getting close to the Earth. And they have all the benefits and hazard associated with that. And so I really want to talk about how we go about looking for these, what we do with the information we gather about them, and then what happens in the case that there is a hazard that they pose to us. And so this is just in the opening image here. This is from the NASA's DART mission, which rammed into Dimorphos. That's the small moon on the left here. Which is orbiting around the near-Earth object Didymos on the right there. And you can already see some unusual properties just from this snapshot image of these bodies. Didymos is this weird elongated thing with this central ridge. Dimorphos is a blocky rubble pile thing that's also kind of egg-shaped. You can see a smooth feature along the equator of Didymos. Almost as though material has been sliding down and that the dust is sliding what to our eye looks to be uphill. Now, because this is spinning, it's actually at a gravitational low, and so things want to roll down towards the equator. And for some of the objects of this size and this class, the surface gravity right at that equator edge is near zero. And so material will roll down, gather, and then can get lifted off. And that's how we think this moon Dimorphos formed. But what this is all telling us is that near-Earth objects are these dynamic systems, and we need to find them, but we also need to characterize them. We need to figure out what it is that's going on with them. How fast are they rotating? How coherent are they? Because all of this matters for what we're going to do if we ever find a hazardous one. And so I want to start. I really like this image that Emily Lakdawala put together. This is quite a few years old now. At the time, it was all of the asteroids that we had visited with spacecraft. But what she did when she put this together is she scaled them so the sizes are all comparable, are all correct. And the colors are as well. And so this is what your eye would see if you were on the spacecraft that flew by them. And so we have a range of objects from tiny Itokawa there that the Japanese Hayabusa mission visited, all the way to this large asteroid Lutetia that ESA's Rosetta mission went to. And then you have some dark material as well. Matilda over there in the bottom right is this large, heavily cratered thing. That shadowed region is a crater almost the same size as Matilda itself. And that is speaking to a very weak, internally porous material that can absorb a lot of impact without breaking. At the bottom, you also see the comets that we've flown by. And these surfaces of these objects are uniformly dark, very similar to these dark objects like Matilda, which is no accident. They have very similar surface compositions, although they formed in slightly different regions, we think, and have had very different histories in the 4.5 billion years since their formation. But from these images that we're seeing, we see a variety of worlds, this diversity of histories exposed to us. So you can see, again, Matilda with that giant crater on it, compared with Lutetia, which looks more like, a knobbly version of the moon. You have some smaller craters. You can see a few bigger craters that have been worn down over time. But there's a dynamic environment happening here. With striations, you can see chains of craters emanating out where material is getting knocked off and falling back on the surface. And so the big objects here, specifically Lutetia, Matilda, these are in the main belt. And that's the material that then feeds forward into our near-Earth population. So if we do look at a top-down view of the solar system, this is what it looks like. Of course, this is, not, the point sizes aren't to scale, but what this is a map of where we are in the solar system. Every dot there is an asteroid or a comet that we're keeping track of, that is at its location at the time this plot was made. The green dots there, these are all the main belt asteroids. That's this reservoir of objects between Mars and Jupiter that's been stable for approximately the lifetime of the solar system. There is some dynamics in there, there is a drain, and so material is coming out slowly, but it is a generally stable area holding these relics of the epoch of planet formation. The red dots are the near-Earth objects. These are things that have, through time and through non-gravitational effects like solar radiation pressure, have had their orbits moved enough that they leave this main belt stable region and go on to planet-crossing orbits, specifically getting close enough to the Earth's orbit that we feel like we should be paying attention to these objects. And what you're seeing here is that there's this cloud of objects all around the Earth's orbit that, again, these points are far bigger than the real objects. Space is, in fact, mostly empty. But they're everywhere. They're all over, and they're constantly moving. The blue dots you see in the bottom left and bottom right, those are the Jupiter Trojans. And so these are objects that are trapped in a one-to-one gravitational resonance with Jupiter. Our best model for their formation today is that very, very early, as the planets were reconfiguring and being built, Jupiter was slowly accreting a core. It was getting bigger and bigger until it hit a critical threshold in the first few million years of our solar system's history, and it was able to suck in gas and go from a 10 Earth mass object up to its current size very rapidly. And what that did is anything that happened to be in those regions, in these Lagrange balance points, was frozen there. And so what we're seeing is this snapshot of the chaotic formation of the minor planets in the solar system at the moment Jupiter grabbed its atmosphere and became the gravitationally dominant body orbiting the sun. The squares here are all of the comets, things that are coming in. Some of them have had gravitational interactions with Jupiter. And so they're having short periods. They go in and out from Jupiter to closer to the sun and back. They have 5, 6, 7 year periods. Whereas the other objects, the open squares, these are things on long period orbits. These are objects that are coming from the Oort cloud and falling into the inner solar system, only to be seen once in our lifetimes or possibly once ever. Some of these will, as they come in, will get a slight gravitational push or will outgas enough material in such a way that they leave the solar system forever. This plot was made, as you see on the bottom, in 2019. This was before we knew about the interstellar objects. We had just discovered Oumuamua, and we hadn't found Borisov quite yet when this was put together. But the interstellar objects then are this same history of small bodies being formed, being moved around gravitationally, sometimes being ejected from their home systems, wandering the galaxy, and then coming into our solar system. And while Oumuamua was hard to track because we only saw it on the way out, 2I Borisov, we were able to get some good data on it. It looked a lot like our Oort cloud comets. The third object, 3I Atlas, was incredibly interesting because based on the direction it came from, the speed it entered our solar system, it looks to be about 10 billion years old. So twice as old as our sun, as our solar system. That was formed at a much different time in our galaxy's history when there was a different set of chemical elements available in the different combinations, when stars hadn't gone through as many supernova cycles as they had when our sun formed. And so we're hoping that as the next generation surveys come on, we get more and more of these interstellar objects, we start to build up a population, we start to build up a census of these, and now we can actually chemically probe different epochs, things that were happening before our sun even formed. But of course, this is not what the solar system looked like a couple hundred years ago. So in 1800, this is what we knew about the solar system. So we knew there was a sun, we knew there were planets going around the sun. We have Mercury, Venus, Earth, Mars, and Jupiter shown here. Saturn we've known about since ancient times. And just a few years before this plot, William and Caroline Herschel had discovered Uranus out beyond Saturn. And that had opened up this new idea that there's other things out there. Right? We knew that there were comets coming in, but people had debated whether they were atmospheric phenomenon or some sort of thing bursting through the glass spheres, holding the planets up. But they were considered outliers and oddballs, but it wasn't thought that there was anything permanent out there until Uranus was found. And that started what's effectively a race to find the next thing, in particular to fill in this gap between Mars and Jupiter. It looked slightly too big for what people were comfortable with and what we wanted there to be, given how small the inner planets are and how big Jupiter is. And so searches were conducted, and shortly after, a new planet was found. Ceres, we named it Ceres, it was great, it solved the problem. But a few decades later, more planets were found. And then a few decades later, more planets were found. And it suddenly went from this case of having a couple of planets, having 6 planets, and then having 7 planets, 8 planets, 9. We got up to around 20 to 30 planets before we realized that there was a belt of bodies, that these weren't unique objects, but instead this represented this reservoir of material. And so as time went on, as technology got better, you can see more and more objects filling in this video until when we get to the 90s, you'll see a sudden uptick in our discovery rate. And this is, of course, due to a few key things that happened. One was that detector technology got a lot better. We had switched from photographic plates and photomultiplier tubes to early CCDs. And once you can take pictures, you can be a lot better at discovery and doing sky surveys. A comet impacted Jupiter. We had Shoemaker-Levy 9 crashing into Jupiter, demonstrating that impacts did happen, not just in the past, but in the present day. We also had, the advent of these new Space Guard surveys. We had the idea that, the dinosaurs were wiped out not by some sort of geological event, but by an asteroid impact. And the identification of the Chicxulub crater being linked to that KT boundary, and the iridium later pointing to something that was extraterrestrial, that was from beyond our Earth. All of this implying that there were impact threats out there. And then really the most important thing that happened in the 90s to cause this sudden upswell in discovery of asteroids was the release of the movie Armageddon, because it brought this into the public sphere. It got this out from the science books and into the world where the public understood it. Now, the movie Deep Impact came out around the same time on a very similar topic. It was much more scientifically accurate, but it didn't have Bruce Willis or Liv Tyler or an Aerosmith song, and so no one remembers that one, and everyone talks about Armageddon. So, there's something to be said for star power in this. But regardless, it did cause this sudden appreciation in the public. All of these factors kind of came together, and people said, hey, we should be doing something about this. And so NASA started doing something about it. They started funding surveys specifically to look for asteroids. It went from hobby projects of small researchers to these very large professional surveys of the sky specifically designed to find moving objects. And so that's why we got to the state we're at today, where we've, based on the surveys we've conducted and our analysis of the data that we've obtained, we can say that we found over 90% of the dinosaur killer objects out there, the things a kilometer in size or larger. have been identified, are cataloged, and have been shown that they won't impact the Earth. And so that's a really good spot to be. We would like to get to the next step of things that could, wipe out state or a large metro area. And so that's our next step that we're working on. So these near-Earth objects, these things that are threats to us, what are they? Like what? These, as I said, the asteroids in the main belt are these relics of planet formation. These are, the analogy I like to use is you can go to the asteroid belt and you can look at this and you can see the materials that went into building the Earth and building Jupiter without having to rip them open. The same way you can go to a construction site for a house and you can look at the nails that were left behind and the end cuts of the 2x4s and little pieces of insulation that were left behind, and you can see what's inside that house. How is it put together? It takes some work and you got to make some guesses, but you have your materials, if you're clever about it, laid out in front of you. In the same way, the asteroids provide us that same look into what was going on in the early solar system, because they've been roughly frozen in time since that moment, epoch of formation. Now, much like those nails in the analogy, weathering, rust, exposure to the elements changes their surfaces a little bit, but fundamentally, you can still learn about what's going on with them. And it's the same for asteroids. The sun baking on them does change the materials. They crash into each other. That's why we have craters. And a lot of the near-Earth objects, as you're seeing here, these are the three that have been not just visited by spacecraft, but had samples brought back from them. So in the bottom, Hayabusa visited the Itokawa asteroid. On the left, OSIRIS-REx visited Bennu. And on the right, Hayabusa 2 went to go see the asteroid Ryugu. Now, Itokawa on the bottom is a silicate asteroid, an S-type we call it. And so that has materials very similar to the rocks you'll find around, with similar input materials as the rocks that Earth is made of. It's, silicon oxides, magnesium, iron, a lot of the similar materials. And we think that the S-types possibly were one of the either formed near or at the same location as the early things that gathered to form the Earth later. The other two objects are actually these dark materials that we think formed much further from the sun, possibly even outside of Jupiter, and were brought in during that early epoch of reshuffling the solar system. But in all these cases, what's unique about these objects is how they look like crushed up gravel piles. And that's because they're crushed up gravel piles. These things are relics of large impacts that happened between these multi-kilometer sized bodies, and the material that was shot out slowly reaccreted in the empty vacuum of space, building these very weak structures. And so if you look at Itokawa on the bottom there, it looks kind of like two potatoes stuck together with like an egg in, like, there's a neck region in the middle that might have some flow. There's some dust here, but there's a giant boulder sitting on the edge over here. All of this is showing how weak that surface gravity is, that there's very little substance to it. And so if we had to interact with these bodies, if we had to move them out of the way should they pose a hazard to Earth, we need to understand how we would do that. If you've ever gone to a firing range, you fire a bullet into a sandbank, the sandbank doesn't care. It will take the energy of the bullet and not move. Versus if you fire at something solid, you'll have a lot different interaction with the surface. You can knock solid things off, you can break them in a way that a loose rubble pile won't respond. And so we need to understand these properties in order to figure out what we're going to do in the case that one of these is coming at the Earth. But even beyond that, just the fact that they were formed this way and then reaccreted, but they've undergone a shock, they underwent a collision, but they really weren't heated in the process. And so they still are fairly pristine samples of this early solar system, of the history of the early solar system. And so that's why we sent 2 spacecraft to go bring back samples of these dark materials, is that tracks where all of the early volatiles were. Where was the water? Where was the carbon dioxide? Where was the material that we think came into the early solar system right after the Earth had formed, when it was so hot that any water that was initially there got boiled off and blown away into space? All of this carbon material that was the building blocks for life, all of the water that came in to become our oceans, probably came from these kinds of objects crashing into the surface of the Earth in the first 100 million years of the solar system's history. Now, these objects do in fact pose a hazard to us. So they do cross Earth's orbit and they do impact Earth. And it's not just in the past, it's not just other places. We have impacts here on Earth every day. This is a map. You can get this at the JPL webpage listed in the bottom left, the Center for Near Earth Objects. And I love the title of this. They call it, reported by U.S. government sensors, which is a euphemistic way of saying the Nuclear Weapons Tests Ban Treaty monitoring satellites. So these are things that were put up in orbit looking for large releases of energy, indicating that someone's testing a nuclear bomb somewhere. And what happens is they pick up all kinds of things that aren't nuclear tests as well. And so what I'm showing here, this is everything that's hit the Earth from 1988 to a few days ago as a function of impact energy, with everything here being a kiloton or bigger. And so these are all fairly substantial impacts. Many of them are high up in the atmosphere. Many of them are over the ocean or over rural areas where no one notices them. But some of them do appear and do show up and are noticed by people. You may note that there's one big red one right over here. That looks pretty interesting. So that's the biggest impact that we've had since these sensors went online, and probably the second biggest one in recorded history after the Tunguska explosion over 100 years ago in Siberia. But this was the Chelyabinsk event. So in February 15th, 2013, early in the morning, Chelyabinsk time, a asteroid probably the size of a house, so we think it was of order 50 feet across or so, entered in at a low angle coming from the direction of the sun over the town of Chelyabinsk, Russia. And within hours, videos were filling YouTube from all different directions and points of view. People were submitting these of this event because of how amazing it was and how awesome the videos were of this giant boloid coming in and then exploding. And you see the trail left behind here and then flashes of light as it released the energy, as it finally got enough atmospheric pressure to be ripped apart and explode. Now, the reason there were so many videos, of course, is that there's a ton of dash cams in Russia because of rampant insurance fraud. And so people would fake accidents or fake injuries or sue each other. So everyone had dash cams, and so people were filming constantly, and you had multiple views of this one event. And you could very quickly triangulate it, figure out how high it was. You could see from multiple cities where these impacts were, where this flash of light, what was the delay between the light and the sound. And you could learn a lot about this impact. It was an incredibly well-monitored one and very well instrumented. Again, because of insurance fraud. But one of the problems with this is that, there was this giant flashing light in the sky. And I'll preface this, as far as we know, no one died from it. But thousands of people were injured by the Chelyabinsk blast because it actually exploded above the sky, in the sky above the city, and sent a blast wave down. I think in the city itself, it was about 90 seconds to 120 seconds after the flash of light. And the problem was that in the 50s and 60s, if any of you remember those days, they had trainings, drills, where you would hide under your desk at school to protect yourself from the nuclear bombs that would fall, that were being dropped by one side on the other. Of course, the desk wasn't nuclear bomb-proof. This was so that when the blast wave hit a few minutes later and the building collapsed, you were under something safe. We live, I hope, in a better time where we're not doing those trainings in school, which is great. However, that means that people missed that message. And so in the era of cell phones, when people saw a giant flashing light in the sky, their first instinct was to pull out their phone and walk up to the biggest window they could to take a video of it. This meant that 90 seconds later, when the blast wave hit, everyone was standing by plate glass windows or just outside the building under as glass fell on them. So the moral, of course, of the Chelyabinsk story is if you see flashing lights in the sky, don't go to the windows, go away from the windows. That's my PSA for this event, or one of my PSAs for this event. But what happened with Chelyabinsk as well is because it exploded in the sky above, and it was February, so had just snowed in Chelyabinsk, the ground was littered with these holes. It looked like someone had stuck their finger all over the snow, and at the bottom of each of these finger dimples was a small pebble. And in fact, it was a meteorite, such as this one here that I picked up. And so this is a piece of that Chelyabinsk meteorite. As it exploded over Russia, it fell, and people would gather them up and sell them to meteorite dealers, who then sell them to collectors. And so you can buy pieces of this object. Now, I do like to reference one other interesting tidbit, and the city of Chelyabinsk has a very particular industry that isn't well known. In fact, it was so not well known that prior to the fall of the Berlin Wall, Chelyabinsk was not allowed to appear on maps because of what they did there. So it was a city where uranium was enriched for weapons, and as far as I know, still is today. And so this leads to kind of an unusual case where you had very early in the morning, just before the sun rose, a explosion, 30, 50 kiloton explosion over one of your main weapons processing cities. And I'm sure there were some very interesting phone calls that happened that morning going around the Russian government. Now, had this happened 50 years earlier, during the Cuban Missile Crisis, the response might have been different. Instead of waiting to see what had happened or waiting to, get more information, there may have been more of a knee-jerk response. And so let's all be grateful that we live in a time where we're not quite as hair-trigger as we used to be. Because the reports from the people on the ground were that there was this massive explosion, the windows were blown out, and then it sounded like they were being surrounded by gunfire, that there was gunfire in all directions, these booms coming from surrounding the city. Of course, when you think about it for a second, what that was is the echoes of that giant explosion bouncing off of every hill and mountain and tree around them were filling the city with the sound, this popping sounds in all directions. But the citizens initially were incredibly worried that they were under attack from someone. So again, another reason to find even the small ones, even the ones that don't necessarily pose a hazard to us as a civilization, is so that we can warn people. Because if 24 hours before this had happened, we'd been able to alert people and say, this is about to come, stay away from the windows at this time of day, and here's what to expect, the response will be different. People will be prepared. People will set up cameras outside away from windows to get really good photos of everything. And so it's another one of the drivers of why we search for near-Earth objects, is even in the case where we only have a short warning time, we can still do disaster management. The same way, if you have a couple days warning for a hurricane, you can make sure that people are safe, that your institutions are safe. We can do the same civil defense for asteroid impacts as well, if they're small enough. And so that's another driver for why we do this kind of science. Now, of course, I have to put in an image of the dinosaur killing impact, knocking material and wiping out all the non-avian dinosaurs. It's obligatory for these kind of talks. But it's not facetious, right? This did happen, and it will happen again. It might not be for millions of years, and if we can do something about it, we can stop it. But the solar system is a chaotic place, and a 6-mile wide object isn't as rare as you might like it to be, given the potentially catastrophic effects it can have on our biosphere, on our planet. And so, again, another reason to not just do a survey once, but to maintain constant vigilance, to continually look for new things, new threats, new objects coming from the distant reaches of the solar system, is that if we find it early, enough, we can stop this kind of thing. Even a giant impact like this, with 30 years of warning, we can do something about that. If you have 15 minutes, you can. And so the earlier you find things, the sooner you do the surveys, and the more information you have about the body, the more you can do to prevent something truly catastrophic. Now, as I mentioned before, asteroids and comets are not just a hazard to Earth. In 1994, the comet Shoemaker-Levy 9, that's a typo there, comet Shoemaker-Levy 9 impacted Jupiter. And so this was a comet that had to swing by Jupiter, and it was ripped apart by tidal forces. And then it went on a half an orbit and then crashed into Jupiter a short time later. But we had seen the object as it had swung by Jupiter and as it was ripped apart, and we were able to track its orbit then. And so we were able to predict when this would happen. Now, no one knew what was going to happen. This was a small object. It was, a few kilometers in size. Jupiter's a giant planet. It's a gas giant. It's the big bully of the solar system. We weren't really sure what to expect, but we trained our telescopes on it anyway. On the left, you can see a sequence of images from the with PIC 2 from Hubble. The impacts did happen just over the limb from where we could see. So the impact was behind the edge of the planet when we saw it. But Hubble was able to get images of the plumes of one of the impact erupting up from the surface, from just over the limb as it impacted. But what was even cooler is as Jupiter rotated and the cloud deck came into view, we were able to see the effects of these relatively small objects hitting this rather large body. And what happened, what we got in the top right there, is this chain of black eyes across the surface of Jupiter. Now, what's really amazing, of course, is that each of those holes, each of those wounds on Jupiter's cloud deck is the size of our planet. And so a small object can have a massive impact just because of the velocity, right? Mass times velocity squared. So if you're moving fast, you can do a lot of damage. And that's told true by the bottom image there. This is from an infrared camera, and you can see the thermal heat that was injected into Jupiter's atmosphere at each of these locations that stuck around for quite a while as the atmosphere was roiled by this impact event. And so if this happens again, we'd rather know about it in advance because we can study it, but it's part of our information gathering about what the state of our solar system is and what we can expect out of it. Now, again, all of these things are in the fair bit of past, and for the younger members in the audience, you might not remember any of that, but this one you will remember because this was only a couple years ago. So in December of 2024, a new near-Earth object was found. 2024 YR4 was the license plate code it was given. And what happened was, this, for the first time that we've been doing this survey, an object of significant size rose to an impact risk that required us to activate our protocols for notifying the White House and the International Astronomical Union. And so what I'm showing on the left here, these are the discovery images from the Atlas telescope. And you can see circled in green there is each of the individual images of the object. And so it was reporting those measurements to the Minor Planet Center. When the Atlas survey reported to the Minor Planet Center, they were able to calculate that this orbit had a potential for hitting the Earth. And so that's that first red point you see on the bottom right on the left plot. And so what this is, B-plane uncertainty, this is how well we know where it's going to be in the future when it crosses the Earth's orbit. And on the y-axis there is the likelihood that that object will hit the Earth. And so when you discover an object like this, the uncertainties from forward predicting its current position into a future position wind up making a line on the sky. And if that line crosses the Earth at a specific time, that's an impact probability. And so you can just ask what fraction of that line is crossing the Earth, and that's your impact probability for this whole uncertainty region. So you can see it started out at less than 1%. And what we anticipate to happen is that the discovery path will follow one of these black curves depending on how close to the Earth it gets. And so as we get more information about the future orbit of the object, that line in the sky gets smaller and smaller. And what it means is that the fraction of that line covered by the Earth gets bigger and bigger, causing the impact probability to rise and rise and rise up until the point that that line falls off of the Earth and then it drops to zero. And so that's exactly what we saw for YR4, but it took some time to do this. And so it had dropped from 3% impact, so it was discovered in 2024, and then it got to up to a 3% chance of impacting the Earth in 2032, before a coordinated effort of ground and space-based telescopes allowed us to rule out the fact that this is going to hit the Earth. And so we're able to entirely remove the chance that it was going to hit the Earth in 2032, which is really good news. But there was still a chance, even after we ruled out Earth impact, that it might hit the moon. And that actually got up to around 4.3% of hitting the moon on December 22nd, 2032. Subsequent observations, so we were able to, the community was able to get the James Webb Space Telescope to take special observations of this object to record a position when it was fainter than any ground-based telescope could get, to measure the exact position And we were able to use those data to rule out a lunar impact in 2032 as well. Frankly, I was kind of rooting for a lunar impact because that would be pretty cool to see, have that kind of prediction in advance and maybe station some telescopes to look at it, potentially even see it naked eye from the ground. Sadly, that's not the case. But, it's better that things aren't going to hit the Earth and the Moon. But, this is just to point out that we are watching and we're exercising our system. We've done a series of exercises. Every 2 years, the community gets together for something called the Planetary Defense Conference, where we go through what would happen if. What happens if we find something that's doing this? What happens if we find this kind of object, or we have this subset of information? And so we go through these tabletop exercises, and then when real cases happen, we're able to execute on them. And so this really showed us, how this works in the real world. If we ever did find something that is going to hit the Earth, what process will we do? It generally worked pretty well. There were a few hiccups in it that we've learned lessons from, but generally we have, started to exercise this global system of monitoring for objects coming close to the Earth, and that might pose a hazard to us. So, of course, the question then is, what do you do? Let's say you do have an impactor and it is 100% chance of hitting the Earth. What do you do? Well, the two fundamental questions are, how big is it? Because that dictates how dangerous the impact is going to be. What's the potential for damage? And then how long do you have? If you only have a couple days, there's very little you can do, frankly. And so all you're left with is civil defense. You clear out the impact zone, you prepare supplies outside of the blast radius to bring in, you get people safe, you take what you can out, and you try and harden what can't be moved. But if you have years, if you have decades, a whole bunch of other options open. And then again, it depends a lot on the size, but one of the options we've been talking about a lot is a kinetic impactor. And this is kind of the simplest thing. You take a spacecraft, a big chunk of copper, and you just put it out there in space and you ram it into the object, and you hope that there's enough energy in that impact to move the orbit of the object off of its impact trajectory with Earth. Now, this is a really hard thing to do, right? You're talking about things moving tens of miles every second through space, where you have a small object against a star background, and you have to do a lot of onboard navigation. You can't rely on the ground. And so, it's a fairly complex system. And so we wanted to test this. And so that is what the DART mission was all about. It was an attempt to take a spacecraft and actually run into an object of a size that a potentially hazardous asteroid would have, to see if we could actually hit the thing. If we hit it, how far could we move it? Could we move it as enough to measure it, a measurable amount? And would that amount be what we would need to prevent an impact? The reason Dimorphos was chosen is that it was a moon of Didymos. Didymos, being bigger, had a much more well-known orbit and was easier to track on. And so we were able to discover Didymos, then find Dimorphos, and then launch to that orbit. So we had a broader suite of telescopes we could use to track Didymos before we sent the spacecraft to Dimorphos. And so what happened was we were able to execute this experiment. And so what we're seeing here is a video returned by the DART spacecraft as it's approaching Dimorphos. So Didymos is in the bottom left. Again, this is the opening slide. And Dimorphos is right in the center of the field of view. And you can see as the spacecraft is readjusting its trajectory as it's coming in on final approach. And so this is all autonomous. This is all on board. And you can see as we're getting closer and closer just how weird this world is. Just how strange of a gravelly surface. Now we've hit into the real-time, this is the real-time images as they were coming back, until we get to the final image that was only partially returned before the spacecraft was destroyed on impact with Dimorphos. And so it was a success, right? We did hit Dimorphos. We did cause a giant crater on it. We kicked up a plume of material that was seen from telescopes around the world. We were able to measure that we did indeed change the orbit of Dimorphos around Didymos. Again, another reason to hit a binary moon is that it's very easy to check what that change in energy was very quickly. So we're able to demonstrate that yes, DART worked, DART moved the target. And now we're going to send, ESA, in conjunction with NASA, is sending a spacecraft called Hera over to the system to take a look at what happened after. How did this material, this plume of material that went up, did it fall back? How did it change the surface? What does Dimorphos look like today? Right? How much did it change that structure? Because of that rubble pile structure that it looked like it had, how did that body respond to that impact? And so we're going to learn a lot once Hera gets there. I believe it gets there in a year or so, of, how do these objects respond to these sudden impulses? Because that lets us plan the next mission, should we ever need one. So I've been talking a lot about the hazard posed by asteroids, and about the history that they can tell us about. But there is another thing that near-Earth objects offer that is oftentimes brought up in specifically science fiction, but is starting to be talked about more in engineering firms around the world. And that's this idea that near-Earth objects could be a resource for us to use in space. Right? One of the reasons space travel is so expensive is because you have to take all the stuff you need off the ground. You have to take it out of Earth's gravity well and huck it into space before you can even touch it, before you can do anything with it. And so if there's anything you can get in situ from the places we're exploring, that is something you don't have to pay to take off of Earth. So you might hear people talking about, oh, let's go to an asteroid and mine some sort of rare metal like iridium or platinum and bring it back to Earth, or bring 1,000 pounds of platinum back to the Earth, and then we'll all be rich. If you brought back a couple tons of platinum, I assume that would crash the platinum market, and then it wouldn't be worth as much as it was when you launched the spacecraft. But also, it's pretty expensive to go there and bring stuff back to Earth. For example, the OSIRIS-REx mission brought back 120 grams of sample from the asteroid Bennu, and it cost $1 billion. So whatever you're bringing back has to be awfully valuable for the economics of that to work. But using the resources that you find there on the way in space is much more valuable. And in fact, one of the most useful things that you could do in terms of asteroid mining would be extracting water from these objects. Because if you're going to send people into space, if you're going to have long-term settlements anywhere, you need water. You need water for people to drink. You need water to grow crops. You need water to split into hydrogen and oxygen to turn into fuel. It solves a lot of problems if you can get it. And one of the things we learned from those Bennu samples that were brought back, you can see a microscopic image zoom in of two of the small pieces. Those bright crystals are phosphates. These are things that formed in a briny environment, because objects like Bennu here were actually warmed up during their formation and kind of started out life as mud balls. And so there's a lot of water caught up in these materials, and a lot of materials that could be very useful for a variety of constructions. So if we just look at that Bennu material, it's about 80% phyllosilicates by composition, 10% sulfides, 5% magnetite, 3% carbonates. All of these things are materials that go into constructing, say, concrete, right? You can extract water. By mass, these things are 10% water. And so all you have to do is grab some sample of this, bake it in the sunlight, and you could sustain the water needs of a small colony from a moderate-sized near-Earth object. And so this is, again, this is still somewhat sci-fi, but every year it gets a little bit closer. This isn't quite as long distance as, warp engines or anything that's kind of very far future. This is just nearly within our grasp. And so I'm excited to see what, a lot of the new space technology that's being developed, where it goes with this. But before you can mine them, before you can calculate their hazard, before you can hit them with DART, you have to find them. And that's the mission I'm working on now, is the Near-Earth Object Surveyor mission. So this is our next generation space telescope. You can see an artist concept of it on the left there. This is led by our PI, Amy Meinzer. She's a professor at UCLA. And this is a 50 centimeter telescope. It's frankly not that big. The whole structure, though, in order to take the images we want and do the science we want, needs to be, it's about the size of it, 20 feet long, so it's kind of 2 stories high. It's comparable in size actually to a Cybertruck. To carry up what's effectively a 50 centimeter telescope that has 2 detector arrays, each the size of a candy bar. And so these are two 16 megapixel arrays, and they're technology called mercury cadmium telluride that allow us to sense infrared light. And so specifically, we're taking images at two different band passes simultaneously, between 4 and 5 microns and between 6 and 10 microns. And what that does is that measures the heat being emitted from these objects, from these near-Earth objects. And that heat allows us to easily detect them against the cold background of space, but also to measure their sizes. To do this, we're going to launch this satellite to the Earth-Sun L1 orbit. That's the gravitational balance point between the Earth and the Sun. It's about 4 or 5 lunar distances away from the Earth. So it's not that far away, which is good because it means we can downlink the data quickly. And so we can take these full-frame images, get all the data down to Earth, and then it gets sent to us here at IPAC, and we're able to process it quickly to report the positions of the objects that we detect, and then archive this for future use for the public to use. Now, one of the lessons we learned from NEOWISE, the WISE mission, when it went up, was fabulous at detecting asteroids, but it was cooled down to just a few Kelvin by a solid hydrogen ice. And when that ran out, we lost a lot of our sensitivity. So we've designed NeoSurveyor to operate with passive cooling. So that's why you have this giant black box there, is that's radiating heat into space with the goal of getting this entire system down to 40 Kelvin, 40 degrees above absolute zero. And that allows us to use the detectors where they're not emitting light at the wavelengths we're interested in. If our detectors are cold and our telescope is cold, then our telescope isn't glowing at these infrared wavelengths. Based on the simulations we've done, we anticipate detecting around 300,000 near-Earth objects. It's about a factor of 10 more than currently known. And over 8 million objects in that main belt between Mars and Jupiter. It's about a factor of 5 more than the current surveys that all surveys up till now have discovered. And that's anticipated during the 5-year prime survey, but we're designing this to go longer. We've put no consumables on board other than hydrazine for station keeping maneuvers and for dumping momentum. So we've been instructed by NASA not to make any decisions that would limit the life to less than 12 years. Because once you put an asset like this up, the idea is to just continue to do the survey, continue to keep a watch on the solar system to make sure that we know where these things are going and can predict any future impacts. As I mentioned, this is really expanding on all of the lessons learned from NEOWISE in order to build a comprehensive census of hazardous NEOs. And we're currently in construction right now. Actually, that whole black box is fully assembled and is just about to be rolled into a cryogenic vacuum test chamber in Logan, Utah, where it's going to undergo its final ground testing before it gets integrated with the spacecraft bus and gets launched from Florida by May of 2028. And so I work at IPAC here at Caltech, and we host the Survey Data Center, as well as the archive, the URSA archive. We're going to be putting all of the images and all of the source detections that we make. So NeoSurveyor's power is its ability to look close to the sun. That sharp angular feature was designed that way so that we can look down 45 degrees from the sun. So those blue windows there are the zones that NeoSurveyor can operate in. And you'll notice the difference is with a ground-based telescope, if you're looking at the night sky, you have to be looking away from the sun. But objects that pose a hazard to Earth like to hang out near Earth's orbit. And so by looking into the daytime sky, what we're doing is we're looking along the path of the Earth for things that might have future cross-ins. And that's why it's such a powerful system, despite being a fairly modest-sized telescope. Comparing this to NEOWISE, that tan zone you see, NEOWISE had a very narrow field of view. It couldn't look much closer than 90 degrees from the sun or much farther from it because of the way that the telescope was designed. It was never designed to look at asteroids. And so what we're doing is we're expanding the observable window, and then that pushes out how deep we can go. And the limit that we can detect objects at this 140-meter class that we define as the next ballpark for what we want to find the hazard, where we want to constrain the hazard. Again, being at L1 lets us be close enough to download all of the data that we're taking, but keeps us far enough from the Earth that we're not getting thermal heat load. The Earth isn't warming us up. And so this is what asteroids will look like in the infrared. So here at IPAC, we've made a very detailed image simulator that takes all of the lessons we've learned from WISE, all of the data, the sky maps made by WISE, and then turns them into simulated images. So this is one of those WISE image sets that we use to build on that. And you can see these repeated views of the sky. The asteroids will move against the background. And so all you have to do is take a series of images and then you connect the dots basically. And so what you're doing is programmatically looking for the things that are moving against this fixed background of stars. Now, because of the wavelengths we're looking at, all stars, whether they're blue stars or red giants, appear blue because we are so far out into the infrared that everything is on the Rayleigh-Jeans tail of the spectral energy distribution, except for these asteroids that are around room temperature. And so room temperature things will glow as these bright red sources against this blue stellar background. And so even just the color of the objects allows us to quickly identify what are the moving objects in each frame and helps us improve our linking abilities. So you can see the two big asteroids here in the middle, but if you look closely at the image, you'll see other chains of dots filling up the sky. And in fact, asteroids are the brightest things in the sky at these wavelengths. Stars tend to fade out, and the solar system suddenly booms in appearance. And so this really is the best place to go searching for these objects. And this is highlighted here in this spectral energy distribution. So on the bottom here, I'm showing wavelength in microns. So your eye can see stuff off all the way at the left here. And then the blue band and the red band here are the band passes that NeoSurveyor will be operating at. These solid lines show the flux that we expect to get from 3 different near-Earth objects, depending on how reflective they are. And so this solid line down here is that dark material, like a comet core, like asteroid Matilda or Bennu. Whereas this higher, the small dash line at the top here is something more reflective, like Itokawa, this silicate-rich material. And what's really, what this highlights is that asteroids, most of their energy is coming out in these infrared wavelengths. And so you really are looking where the asteroids are the brightest. But the other really great thing is this thin line here. This is showing the number of stars in the sky brighter than this NEO as a function of wavelength. And so in the optical, for every near-Earth object you're looking at, there's thousands or tens of thousands of stars comparably bright. When you get out to this 10 micron zone here, there's handfuls. All of a sudden, the stars have gone. And across the entire sky, there's only a few objects that are even comparably bright to the objects we're looking for. And so again, this really is, shooting fish in a barrel kind of hunting, which is great when you're designing a survey that's supposed to find things that pose a hazard to us. So this is another top-down view of the solar system. I forgot to put the sun in the middle here, sorry about that. But this is showing what we anticipate the first 5 years of survey to look like. And so as this goes on, you'll see each of the white flashes is the first detection of a new near-Earth object that our survey picks up and records its orbit for, putting into the catalog. And then the green dots are just that catalog being built over time. And what you see is that we're just conducting this survey over and over, first leading side of the sun of the Earth's orbit, then the trailing side of the orbit, back and forth in this regular pattern, specifically designed to get as much information as possible about these objects and to track their orbits so that we know where they're going. So what's really interesting about this, in this simulation, I'm only showing the near-Earth objects larger than 140 meters. That's the ones we're really interested in as the truly big hazards. There'll be about a factor of 10 more smaller near-Earth objects that we detect, and a factor of 1,000 more main belt asteroids that we detect. And so this is going to be an incredible powerhouse for really understanding our solar system going forward. So here's a few images of the instrument being built and tested. And so you can see it's this sharp angular feature here allows us to point down to 45 degrees from the sun without getting any sunlight on these really sensitive panels that are supposed to be radiating heat into space. And this is the entrance aperture. It's actually a 3-mirror and a stigmat design, so we have no spider, which helps us avoid diffraction spikes. one of the lessons we learned from NEOWISE is that the moon, being warm and bright, had diffraction spikes in the NEOWISE images that went out to 60 degrees away from the moon itself. And so we were getting these massive diffraction spikes across the sky, even though we were pointed nowhere near it, just because of how bright it was. And so that was one of the design choices we made for NeoSurveyor. And then just in here, just behind that, that plate there you see below the entrance aperture is where the two detector banks are living, where the instrument is. And so this was over at Johnson Chamber A. We were doing some thermal balance tests to make sure that our predictions for how this spacecraft setup would respond to heat and that it could actually get rid of the heat that we anticipated it receiving from the sun, that all of that actually matched reality. So we built the thing and actually tested it and showed that our thermal balance was accurate to the models that we made. So that was a really good validation. Now, how can you get this data? So the WISE data and the NEOWISE data are available right now, and they will be at the same interfaces that the NeoSurveyor data will be available as well. And so I encourage you all to use these if you're interested. This is not just for science. You can do anything with it. We have people making pretty pictures. I've seen people download these images and make art with them. This is public data because it was funded by you, the taxpayers. So, we really want to make it as easy to access and make it as available as possible to everyone. And so you can go onto the Infrared Science Archive that we host here at IPAC, download all of the images that were obtained by the WISE mission, both of static sources in the sky as well as moving objects. This is just showing an image of an asteroid that was this was the first asteroid that we discovered with WISE back in 2010. And the same interfaces will be used for getting data from NeoSurveyor. So if you test out the WISE interfaces, you'll be ready for as soon as our data releases start with NeoSurveyor. So just in closing, we're really entering a new era of near-Earth object science. Ground-based surveys like ATLAS and PanSTARRS and the Rubens LSST survey that's coming online right now, in addition to NeoSurveyor, are going to perform the most detailed census of asteroids and comets ever. We're finally going to really have a good idea of who our nearest neighbors are in the solar system, where they're going, and what they're made of. After it launches, NeoSurveyor is going to allow us to find over 90% of all the potentially hazardous asteroids, down to 140 meters in size. This is the next hurdle that we've been instructed by Congress to solve. And infrared surveys in particular give us the ability to determine the physical properties of these objects. By looking, once you know the orbit for an object, you know how far it is from you. And so you can just calculate how much sunlight does it receive, how much heat should it emit, how bright did I observe it, and then you can scale that to figure out how big it is. And so this allows us to immediately get the sizes of these objects. And if any of those other surveys have obtained visible light data on it, then we can get the albedo, its reflectivity, or its color. And that traces its chemical composition, its mineralogical composition, and where in the solar system it formed. And so near-Earth objects really trace this physical and dynamical processes that sculpted our entire solar system, including our Earth since its formation. They're each different freeze frames from different moments in that early chaotic time. And so the more we study them, the more we can really answer the question of where did the Earth come from? How did it get the materials on it that brought life today? And how is the solar system still affecting us today? What threat does it pose and what opportunities does it pose as well? And so with that, I'm happy to take questions. Thank you for your attention.
Very good presentation, sir. I'm wondering, given the great number of potential bodies that you're going to be detecting, do you have some plan in place for classifying all of them? How they'll be identified?
Yeah, so I mean, the first thing we're going to do is measure the orbits and the sizes. And from the first classification is where in orbital space is it? Is it coming from this near-Earth population? Which part of the main belt? Because there's different histories encoded there. Is it coming from that Trojan population? Is it a comet? That's characterization number one. Size allows us to trace you can use that in the population of bodies to look at collisional families. That's one of the things I'm really interested in is as these objects crash into each other, you would expect different amounts of shrapnel, different things to break apart. And they break apart in different ways based on that structure of that original body. And so looking at the size distribution of the particles that are all dynamically associated helps us figure out what their internal compositions are. And as I said, albedo, we also have colleagues of ours will be taking spectra. We'll be looking at light curves to look at how non-spherical these are. So yeah, there's a whole range of things that we're going to be getting out of this that I'm really excited for.
Identified, like not names per se, but some nomenclature for all these new objects?
Yeah, so the Minor Planet Center, we submit tracklets. So just here's a link of 4 or 5 or 6 detections that we are confident are the same thing. We send it to them, and then they assign a license plate to it that is the year with a rolling counter of letters and numbers associated with that. Initially, once you have enough data to constrain the orbit to say, I can predict where it's going to be for quite a while into the future, for decades to come, it's given a number. And that number is then a unique identifier that you can trace its position with, and that links right back to its orbit.
Thank you for your presentation. I really enjoyed it. I just had a couple of questions related to the density of these asteroids, and I'm having a little bit of a tough time kind of wrapping my head around. One, could you kind of compare it to something, and I know they're all different types of materials, but generally something that we could kind of use as a reference. And then two, gravity's pretty weak, and so I just have a hard time. I tend to think of it like a piece of cake or something that's flowing through, and the friction from entering the atmosphere. I don't know how it stays together if
Yeah.
it's just bound together. Let's say it's a 50 meter.
Yep.
I just don't see how a bunch of pebbles just doesn't, but it seems to stay kind of intact, like there's some rigidity to it, and I can't square that in my head. So maybe
Yeah,
you could
no,
just add some color to that. That would.
Absolutely. So on the density question, there's macro density and micro density, right? And so some of these rubble piley looking things are just blocks sitting on each other, and there's voids between them. And so the global density of these asteroids ranges anywhere. Most comets and some of the C-type asteroids are around the density of water, 1 gram per cubic centimeter, 1.5. The silicaty ones, like this Chelyabinsk rock here, this is in the order, a little bit more dense than most of the rocks we have on Earth, primarily because there's more iron in these. The iron on the Earth primarily melted down to our iron core. When the asteroids didn't melt, they have a little bit more iron content, so they'll feel a little bit heavier. That's in the 3 to 4 grams per cubic centimeter. The iron meteorites that you'll get, those are up at 8. So those are fairly dense. It's a big chunk of iron. But we see those get ripped apart too, and so it's not necessarily that you're going to have a 100-meter block of iron that's pure iron, but you might. Some of these objects do appear to have structure. We've seen asteroids that are spinning fast enough that had they not been chemically connected, they should have ripped themselves apart. So some objects have a internal structure that may have just been effectively cold welding over billions of years as these materials sat next to each other and built up a structure to them. But this is why so many meteoroids burn up and shatter, and you get these flashes of light and the big explosions, is because they are structurally weak, and as soon as they crack, they do explode. That doesn't necessarily make them less dangerous to the Earth. Right, we know that air bursting a nuclear bomb is even more effective at destroying the city that it's over than hitting the ground, because you can wipe out a larger area. And so, we know some things make it to the ground directly. The meteor crater in Arizona, that one clearly had a kilometer scale crater on the ground that was caused by a single massive piece that hit. But there's this, but that wasn't iron, right? That was a coherent body. And so again, this is one of the reasons you need to not just find them, but figure out what they are, is because you respond differently if it looks like it's 100 meters of iron versus it's 100 meters of fluffy material.
Thank you.
Dr. Massaro, first of all, thank you so much for a wonderful presentation. It was truly fascinating. From a public policy standpoint, do you expect that if you or your team were to ever discover a significant item which presents a significant threat to actually be disclosed? Or would men and women in green military uniforms suddenly come to your office and tell you that it's national security and it can't be disclosed, and we might not find out until minutes before? Do you have what's your best guess on that?
That's a very common question, and we're right to be skeptical of this. But in this case specifically, as we learned with 2024 YR4, when we discover it, and this will be true for almost anything that poses a significant hazard, when we find it, it's going to have a 1 in 1,000 chance of impacting, or 1 in 10,000 chance of impacting. We discover objects like that all the time. We're posting those. Those are constantly getting posted by the Minor Plan Center to a page saying, hey, can you follow this up? And observers from around the world are already working on it. And 9,999 times out of 10,000, it's not hitting us. And so all of these just get dropped off. Now, occasionally you get one that goes up and up and up. But by the time you've hit that, 1% chance of impact where we have to notify people, it's already been out in the public sphere for weeks. You can't pull that back in. There's enough people, and we have colleagues in ESA, in Japan, in Russia, in Africa, all over the world who are doing these calculations simultaneously, who are all saying, yeah, we all agree that the answers look like this. And so it's really hard to get that back in the box. So public disclosure it'd be hard to hide it. Now, the carefully crafted plans we have of how we would respond, and that it would be a civilian-led thing where all the best scientists would get together and we would work with FEMA and we would work with all the organizations, and we would collaborate on that. Will that actually happen, or will people, will jurisdictional pulls take over? Possibly. But this is one of the things we exercise, right? One of the exercises for the Planetary Defense Conference they did a couple of years ago was, imagine you have this object that's supposed to impact India, and you can run a DART-like mission into it and move it off. But you have to hit it twice, and after the first impact, it's just going to move it so now the target goes over China, and then the second impact moves it off the Earth, and then everyone's safe. How do you convince all the players to let you move that target from something that's not hitting them to something that's hitting them, right? So that's the politically sticky situation, is what do you do where you need to have this long term, or if you're doing a mass driver, right, where you're doing this gravitational tractor where over a 10-year period that target moves. How do you convince the people who aren't in danger now to let you put them in danger briefly as you deal with the global problem? And I don't have a good solution to that, right? I mean, that's not very different from any of the other big global problems we're facing. How do you get people to work together to solve things like climate change? Well, we have to figure that out, right? But that's why we go through these exercises is, okay, let's talk through how we might figure this out so we can get on the same page at least.
Thank you very much for your presentation. I'm from California, and I used to go out in the desert. And can you talk to a little bit how the Goldstone fits into that, the giant array that can go out millions of, I don't know how far, but
Yeah.
a long way to get a picture, a radar picture back to the Earth.
Yeah, the radar images of asteroids are truly fabulous. And that's why the loss of Arecibo hit our community so hard, right? That was a unique facility. And it was so hard to build it initially. The attempts to repair it were just astronomical in cost. And then the loss of it really, it hampered us. It really hamstrung our ability to study these objects. Goldstone has been doing a great job, but it's a smaller dish. I mean, even at 70 meters, it's not 300 meters, right? It's not. So, and so they can only really look out to about a lunar distance. But if an object gets inside that range, bouncing radar light off of it lets you build this very coherent and complex map of the object. And so, I have really good colleagues who've been working on this and trying to study how these objects respond to the radar light, right? Because when we look at an object with optical light, what we're really seeing, when we take a spectrum, when we take a light curve, when we look at the albedo, that's really the upper micron of material. That's all that we can see. the radar can see inside that. They can see centimeters of depth. And so they're measuring, what's that, not just the surface structure, but what's the upper couple centimeters of structure? How compacted is it? How metal rich is it? And so they're doing truly fabulous work. Unfortunately, Goldstone is down for maintenance right now. They had a failure of the telescope that knocked out their radar imaging this year. And then they're supposed to go down, I believe, for like 12 or 18 months of maintenance that unfortunately happened right after this thing is supposed to be fixed. And they're not able to do all of the fixes at the same time because the parts aren't ready yet for the later fix because they weren't anticipating being down now. So unfortunately, Goldstone's going to be down for a little while. But the asteroid radar community is experimenting with doing things like transmitting from Goldstone and receiving at the Green Bank telescope. Our colleagues in Australia are also doing radar imaging. They're starting to work on that. There's some groups in China doing it as well. And so, I think that this is a capacity that we really need to continue to develop. But it's really good work, and it produces this very unique data set, not just from the composition, but from the orbit quality. You get distances and speeds, radial speeds of these objects to centimeter scales that you just can't get, orders of magnitude more precise than anything you can get with other kinds of observations.
Okay, my question is, as you put more and more objects at the Lagrange points, is there danger of interference between satellites or collisions? And is there any thought of removing them from the Lagrange point, perhaps into a dead orbit or something?
Yeah.
And my
So-
joke is, as an Air Force guy, I think the uniforms will be blue.
Well, I think that's under the Space Force realm now. I don't know what color their uniforms are, but yeah, I know there's some jockeying for who gets to be the response there. But no, so we do have a disposal plan. Any satellite you put up has to have a disposal plan. And for the Lagrange points, those are unstable equilibria, L1 and L2. And so if your satellite dies unexpectedly, or when you decide to end the mission, you just stop maintaining the orbit and it will drift away into a sun synchronous orbit, and then it's taken care of. In terms of collisions nowadays, the Lagrange points themselves are mathematical points, but the orbits we maintain around them aren't at the exact Lagrange point. They're in these large looping halos. And those halos are 3 lunar distances wide and 1 lunar distance high. So they're actually pretty giant. They're significantly larger than the low Earth orbit volume. And there's very few satellites out there. There's only, a dozen or so. So no, the bigger concern for impacts is getting out through the Starlink layer to get into that much safer deep space area.
Joe, that was a great presentation. Thank you so much for speaking to our club. I had a question for you about some of those ground-based surveys that you highlighted there, like the Catalina Sky Survey. I've known some researchers there over the years, and then I saw the Vera Rubin that you're talking about coming online pretty soon. Can you speak to how they coordinate? Because sometimes if I talk to the people like the Catalina Survey, they think they're the best in the business. I've talked to people, maybe you're Caltech. Hey, is that just rivalry, academic rivalry, or I mean, could you speak to what type of coordination or lack thereof that exists between them, and what those different entities ground-based do that are different from one another?
Yeah, absolutely. So it's not at the level of rivalry. It's more of a friendly. It's like how you always think your house is better than the neighbor's, right? It's not that. You like the thing that you've built. You built it for a reason. You've addressed. You have designed it and put your heart into it. And so of course everyone thinks their survey is the best. Of course ours is the best. But I let them think that theirs is the best, right? But no. So. The ground-based surveys provide, so the first thing that they provide, we need their visible light measurements in order to get these albedo measurements that we want. That's the first tracer of composition that we can get. And so we're going to work hand in hand with that data set and all of our data is going to the Minor Planet Center in Boston, and that's the clearinghouse that the whole community is going to be drawing from. But the other thing, if you noticed in the image I showed of where Neosurveyor can see, we actually can't see out past in the the nighttime sky because since we're at L1, that's where the Earth is, and it's super bright in infrared wavelengths, and so we don't want to look there. And we even can't look there because then sun would get on the bottom of our spacecraft and overheat us, and it'd be a bad day. So we need them to help maintain and fill in that area. And so what it really will be is a handoff between NeoSurveyor detecting things in what's the daytime sky here, handing them off to the ground-based surveys that will maintain, continue to monitor them, follow them, hand it back to NeoSurveyor in the evening side, in that twilight, and then so on and so forth. And so we really do play well together. We're filling different niches. One of the other things that especially Vera Rubin is going to be fabulous at is finding objects in the more distant reaches of the solar system. So trans-Neptunian objects, I anticipate Vera Rubin is going to make some stunning discoveries out in, beyond Neptune and the Pluto regions. NeoSurveyor actually goes blind outside of Jupiter, because once you get out there, objects get so cold that their peak of their thermal emission moves outside of our 10 micron window. And then we're just a 50 centimeter reflected telescope. So there'll be some massive contributions we can expect from the ground-based surveys out in the centaurs, comet source regions, interstellar objects. There's going to be a lot of interplay between all these surveys. And we're really excited because we're probing different wavelength regimes. And so combined, we get a whole lot more information about these bodies.
Yeah, we're good? Yeah, okay. Okay, cool. Two very quick questions. They're very easy. Yeah, yes and no. I was wondering if another bolide were to happen, what would be the procedures to avoid this, and how long would I have to react to it? And then my second question was, what is your favorite object in the solar system and why?
Ooh, okay. Well, first one's easy. So we've actually discovered, I think the count is up to 12 objects now, where we detected them as asteroids just before they impacted the Earth. Now, most of them were the size, they were huggable, right? They're about a meter in size, they're the size of a desk or a small car. And so they were no threat at all. But those we found 12 to 36 hours before impact. Sometimes you do get enough notice to, call people and wake them up if they're going over somewhere useful. In fact, one of my colleagues, he works for the Pan-STARRS telescope, which observes it from Hawaii, but he lives in Canada, in Toronto area. And Pan-STARRS discovered an asteroid that was coming in over effectively his house. And so at 2 o'clock in the morning, he got a phone call waking him up from his coworkers in Hawaii saying, get up, get your camera out. In like an hour, there's an object that's going to come in over. And so he was able to get a picture of the bolide of the object coming in over his neighborhood effectively. So that was really cool. So we should get more and more of those, especially as NeoSurveyor and Rubin come online. NeoSurveyor is not designed to find things with one-day warning times, right? We're off a couple lunar distances away, and anything coming close to NeoSurveyor is not coming close to the Earth, it's coming close to the L1 point. But the other problem is because we only downlink data once a day, it takes us 36 hours before we know we have an image of an object. So that's not the survey we designed. Surveys like Atlas and Rubin are going to be better at those kind of discoveries. And so for those small things, still, in the huggable size of asteroid, you're going to have 24 hours of warning probably, just because you have to wait till they're close enough for you to be able to see it in your telescopes at all. In terms of my favorite object in the solar system, that's really tough. I would have to go with, so just from a photogenic point of view, like Saturn is my favorite thing to look at with my telescope because, of course, it's the pretty thing. Everyone loves Saturn. It's beautiful. But in terms of my favorite object, I'd probably go with the asteroid 234 Barbara. Partly that was, I did my thesis work on some of that, on Barbara. But Barbara is this weird object where its surface looks like it's covered in a material called spinel. And this is the first materials that formed in our solar system. And what's unusual about it is when you look at it with optical polarimetry, it behaves incredibly strangely. If you look at it with near-infrared polarimetry, it's even stranger. But as far as we can tell, this is this dark object that's covered in a sparkly, glittery diamond surface of the very first solids in the solar system. And just how you formed that and where it formed and what its history is just fascinating to me. And I'd love to learn more about it.
That was awesome. We got it. Me. Oh, me. Joe, thank you so much. Hey, you jumped in. We had somebody that was booked for tonight that couldn't make it. She had to postpone. We weren't going to meet Joe until November, right?
Yeah.
And so, hey, thanks for being the hero. Appreciate it.
You're very
making
welcome.
the change there.
My pleasure.
Next slide. We got a little bit more to go, so thank you very much for showing up tonight.
Thank you so much, Joe.
You're very welcome.
Chris, are you online? Chris Ashford?
Yeah, yes, I am.
Okay, go ahead.
I'll put my video on for you. There. I can't see the slide though. I can only see me. Oh, there we go. All right. Yeah, so okay, I was just gonna voice over that, but that's okay. All right, so we found further damage to the Noble Observatory. Once we've replaced the network switch, then we can start operating it. And we found that neither of the next dome controllers for the shutter and dome rotation are operating. We also found damage to cables, and some of the 12-watt power supplies don't seem to be working either. The surge found its path of least resistance through some of the Ethernet cables. So that's why we've got more damage than we thought. Mouser Electronics has gifted the club $1,000 for electronics replacement parts. So it's great. Thank you to them for that. Expenditure against the 1,047.27 that was authorized by the board is less than $800 so far. And we bought everything. I think we bought everything that we wanted to buy. And so we've underspent that. Today's motion will bring the total so far, and the motion is, well, I'll come to the motion in a minute, but that will bring the total so far to approximately $2,300, which is still below our insurance deductible, which is $2,500, but is above the threshold for executive board approval, which is $1,250. So hence, we felt we've got to bring a motion to the general membership. So we haven't done any imaging yet because we can't open the shutter or rotate the dome. So there is the possibility of further discovery once the dome is repaired. Although we feel that is a low probability, but nevertheless, the risk exists. Replacement control boards from NextDome, they're just under $500 each. They're pretty expensive. We'll be trying to negotiate that price down, hoping that they will take pity on us. So if you go now to the motion, please. Next slide. So the board moves to approve the following repairs to the Noble Observatory. 1, authorize a further $1,000 for repairs to the next dome shutter and dome rotation controllers. And then 2, authorize the procurement through Mouser Electronics of a new Melee mini PC, security camera, cables, 12-watt power supplies. Now, subsequently, after the board agreed to the wording for this, talked to Bob, and he said, well, we want to replace the Pearside mini PC. We're not necessarily going to buy a Melee mini PC. We'll get the best value for money. And there are other mini PCs out there. So perhaps an alternative wording to replace of a new Melee mini PC, just say of a replacement Pearside mini PC. and then that opens up. We don't have to buy a Melee mini PC. We can buy any mini PC that we think is value for money for us. Any questions?
So that's the motion. Before we have discussion, do I hear a second on the motion? Discussion's up.
So the $1,000 that the club is going to vote on, does that include the procurement, the cost of procurement of all that stuff under number 2? Or is that extra?
Yeah, that's extra. But Mauser Electronics has offered up essentially a $1,000 gift voucher, so we can buy. Oh, that's why I use the word procurement, because we're not really buying it. We're just telling them what we need, and then they give it to us. And so that's why there are 2 specific items in the motion.
Yeah, so the motion is authorize another $1,000 for repair, and then they're giving us a voucher to actually purchase this stuff through Mauser Electronics. So we're asking to get this stuff through Mauser and expend up to another $1,000 on the dome. Cables, yeah, essentially, yeah. Other questions, discussion? All right, I know, yeah.
Are you sure $1,000 is going to be enough? Should we authorize a little bit more money than that and hope we don't spend it all?
Well, we already tried not to spend it all. We don't know what else is broken. The only things we haven't been able to test is actual imaging. So, for instance, the camera. It depends what the damage is. I mean, buying a complete new camera or having it repaired by ZWO, that could be a big difference in cost. So we decided we didn't want to ask the general membership for a carte blanche, oh, give us another $3,000, and then that will cover it, because, well, we don't think we're not going to need that much money. We don't think. We think the probability of further damage or further discovery is low. So anyway, that was the discussion in the board. Repair, authorized repairs as we go.
So I have another question. Once we do all of this, will the Noble Observatory be completed, or is there still going to need to be monies given to finish it and make it fully functional?
Can I speak to that, please?
There shouldn't be any more money required. I mean, we spent all the money that was in the original proposal. The hardware's been there for a long time. What we've struggled with is, well, first of all, getting that hardware to be reliable. But having got up past that hurdle, then it's the Bob Circus's time to develop the software required, which I think, and Bob would probably, chime in and say, yeah, it was more difficult than he thought it was going to be. And all that work is being gifted to the club by, licensed to the club by Bob in perpetuity at no cost to the club. So I'm not seeing any more cost.
Bob, go ahead.
Yeah, here's on the imaging train. The imaging train is the pier, the RASA, the camera, guiding, and all that mess. Outside of the telescope, the most expensive part of that imaging train is the camera. What I have been able to do to test the camera, because it's that time, I've run a set of dark frames. So that's close to, I think, 300 dark frames of varying exposures at low temperatures. I've examined those. They look good. The biases look good. And I've taken flats on several occasions to test the flat panel. And so it appears the camera is in good shape. So until we can actually open the dome, we won't know for sure. But operationally, the camera's in good shape. And the thing that I was most worried about was the weather station. The weather station is working perfectly. So I hope that clarifies things.
All right, thanks, Bob. Any other discussion? All right, I know we have a quorum in here, but Chris, can you still count online as well? So we have a motion and a seconded. All in favor of expending the funds as listed on the slide? Raise your hand. Any opposition? None seen. And if you're online, just raise your hand so Chris can see real quickly. You'll get a good count. All right. Motion's carried. Next slide. Yeah, we did that. Buy your tickets. Take a quick break so we can wiggle through the rest of the stuff quickly tonight. 10 minutes. All right. We're gonna do a raffle real quickly. So get your tickets out. I'm gonna do this real quickly. First number 155609. 155609. 609. All right, we got a winner. We got a winner. Next one, 155631. 155631. One 155631. Anyone? Next one. Oh, that's the same number. Next number 155612. 612. All right. Christian. Well, you just take it. All right. 155693. All right, come on up. Next one, 155598. 598. All right, Michelle. Next number, 155605. 605. 605. All right, next one, 155649. 649. All right, Brandon. I'm going to mix these up a little more. I trust you mixed them. Next number, 155682. 682. All righty. You draw four more. 155569. 569. 569. Ah, there we go. All right, we'll mix it up a little bit. 155671. 671. All right. And 155679. 679. Oh, grab another one. Oh, see number. 155606. 606. Nope. 155585. 585. All righty. All right, I'm going to do two more. 155670. 670. No? 155600. 600. All right, Tom. Last two. 155669. 669. All right, last one. 155644. 644. 644. No winners. All right. Next slide, please. Yes. I can't hear you.
I just want to thank Chris Malicki. We partnered with the Thompson Observatory last week, and he did EAA from their TMB. It's it's an outstanding instrument to try and catch the SpaceX. We only had 6,000 viewers across the world on the Fort Worth Astro YouTube channel. And this was a 3-hour or 4-hour event, and I really appreciate him helping out.
Great work.
What?
Great work by all of you. Thanks, Chris. All righty, next slide.
Oh, correction, 60,000.
Yeah, 60,000. 60,000. That's great. A lot of viewers. Next slide. Bill.
Thank you. Check, check. So stuff in the sky for the next month. What we've got featured here is Stephen Kennedy's shot of the seahorse, the dark seahorse nebula, and the squid. Go to the next slide here. This is the full picture of it. Really great shot. That squid was discovered by a French amateur astronomer. So, yeah. Oh, it's like what, OU1 or something is like the name of the object. So, the OU guy, amateur astronomer. Next slide. Bright comets this month. So, 10P Temple is still in the air. It's still in our night sky. It's starting to dim at this point. And 169P NEAT is probably going to be at its best at magnitude 10 in Leo. It's getting a little brighter from here, but magnitude 10 is probably about as good as it's going to go. This, coincidentally, happens to be a picture of the Comet 2020 F3 Neowise. I put it up there because I had a comet picture that I needed to put in the background. It was like, oh yeah, get the Neowise guy. This works out. Cool. Next slide. Occultations and close approaches. So these are both daytime ones, but they're visible daytime ones. So you've got the moon and Jupiter, the less than a degree apart, and you've got the moon and Venus that's about half a degree apart. And if you know where to look in a small telescope, you can see Jupiter and Venus in the sky during the day. So might be a pretty cool opportunity here. Just watch out for the big bright thing. Tyler Dollarhide, this is his shot of last year, January 2025's moon occultation of Mars. Nice shot there. Next slide. I have another asteroid, another near-Earth asteroid for you to go along with the theme of our presenter tonight. This one is 66146 1998 TU3, and this one's going to be closest to us on August 26th. It's a little bit further away at 35 lunar diameters, but it's going to be as bright as 11.5 magnitude. That's on September 2nd. So any details about this or any of the other little guys that are getting close to us, you can, there's the website right here. Next slide. A full moon. August's full moon is on Thursday, August 27th. And Steve Edmonds has this picture of the lunar eclipse. The moon in lunar eclipse. Now, why would I be showing a picture of the moon in lunar eclipse? Next slide. Because 2 weeks after a solar eclipse or before a solar eclipse, just because of alignment, there's going to be a lunar eclipse just about every time. So in this case, it's visible in North America. It's a partial lunar eclipse. You get the umbra all the way till like 93 to 96% of the moon's face, and it starts at moonrise, 8:23. The maximum is at 11:12 p.m. and it ends at about 2 o'clock in the morning. But maximum's about 33 degrees up in the sky, so it's pretty well placed. So that's that. So The entire duration of the thing is 5 hours and 38 minutes, and that is overnight from the night of August 27th to the morning of the 28th. Next slide. So the ninth asteroid that was discovered, it was fun when he was showing the little dots showing up as they were getting discovered on his video there. I was like, oh, there's medicine. There's the other one that I'm going to talk about in a second. So this one, it's opposition on Friday, August 28th. Lots of things happening at the end of August this month here. It's going to be magnitude 9.2 in Aquarius, which is right there. So remember that. Next slide. This is the next night. Astrea, which is number 5, is going to be in opposition. That's going to be in Aquarius as well. And Astrea is right here. Next slide. Metis is right there. You've got a couple of major asteroids next to each other, just a day apart in opposition. So that's pretty cool. Astrea was actually discovered by a Carl Ludwig Hinke. He was a postmaster, and he was an amateur astronomer. And he was looking for Vesta at the time and discovered Astrea. Next slide. Now, the big news. So, Nancy Grace Roman telescope's finally getting launched. It's going to be launched on August 30th at 6:34 in the morning, our time. It's going to be launched from Kennedy Space Center. And next slide. It's heading out to Lagrange, Earth-Sun Lagrange point 2. So does anybody else know, and this is what the telescope's going to look like when it's in space. Does anybody else know what else is floating around at Earth-Sun Lagrange point 2? That's right, James Webb, Gaia, Euclid. There's a few things out there, and he was right about that. Just talking, it's funny how all this stuff ties together, but the orbits are so big that it looks like there'd be a lot of interference or collision or something like that, but there's a lot of space in space. So next slide. September's new moon is on September 10th. Next slide. Not as great as last month's new moon, but we'll make do till next year. So the constellation that I want to feature this month is Little Sagitta, the Arrow. So it's got 7 named stars of such an insignificant constellation in the sky. It's got 7 named stars. It's 86th out of 88. It's 86th in size. There's one Messier object in it, and something I didn't know was Sagitta is not an arrow of Sagittarius. Fun fact. If you're into mythology and you like weird stuff, then this one's for you. So apparently the arrow belonged to Hercules, and what he was doing, what he was poking at the eagle that was gnawing on Prometheus's liver, because Prometheus had stolen fire from the gods and gave it to man, and Zeus was a little upset about that, so he sent an eagle to gnaw on his liver during the daytime, and at nighttime the liver would grow back. And then daytime had come again, and the eagle would start gnawing on his liver again. So that's mythology for you, folks. Next slide. Just, you can't make, well, they did make it up, but, you know. Anyway, don't want to offend anybody's religion out there if they're open-minded like that. Messier 71. So this is also called the angelfish cluster. It was initially thought to be an open cluster, but in the 70s, it was determined to be a sparse globular cluster. So you got to ask, it's like, well, what's the difference between a sparse globular cluster and an open cluster? Well, open clusters are brand new stars. This is the birthplace of stars. Globular clusters are very old, like old in the billions, like old as the known universe sort of age. And what we see is globular clusters actually have the stars have low metallicity. And what that means is the surfaces of them, surfaces of stars actually, unless their atmospheres are blown away, surfaces of stars stay pretty pristine. All the heavy elements and stuff from the fusion that's happening inside the star is happening in the core. And that stuff never like floats to the surface. That stuff only gets out if the star blows up or the atmosphere gets blown away by some other reason. And so, you know, when you see a low metallicity, you're looking at anything that's like heavier than hydrogen, helium. You start getting into the heavier elements and stuff like that. Well, if the it's like when the atmospheres have been polluted. The atmospheres have been polluted, then supernova. So supernova explode, they release this heavy elements and stuff, and it gets into the atmospheres of stars. And when the stars are very, very old, they would, I've just talked myself into a corner. I would suggest that you look it up and learn for yourself. I apologize for the last 2 minutes. They're also horizontal branch stars, very old stars, high mass, and there's a structural concentration. So next slide. And this is Richard Hoffman's picture of Messier 71. Next slide. I can give myself a metallicity lesson and hook you guys up. So the next one is called the Necklace Nebula. So there's a binary reaction, interaction between a giant star that's a binary star with a smaller companion. The smaller companion is orbiting this giant star. The star swelled to outside the orbit of its companion star. So now we've got a companion star, and it's still actually happening. So a companion star is orbiting this star inside the big star. Okay, so what happens when you have that sort of situation is that you have this little star that's inside this big star, and it's orbiting it inside its atmosphere. And what it does is it spins up the star. So now the big star actually increases in rotational speed. And next slide, this is what you get. This is why they call it the Necklace Nebula, obviously. But you've got a spin up, and basically it's just from huge centrifugal forces is spitting out matter, and of course getting ionized by the central star all the same. Interestingly enough, is that the central star is named Necklace, and it was just named in June of 2026. So just a few months ago, the 7th star that was named in Sagittarius. So fun fact. Next slide. So if you've ever seen anything on a star chart that's like M1 and then a dash and a couple of numbers, that's the Minkowski catalog. This particular nebula, it's a beautiful nebula. It was created by a Wolf-Rayet star, WR124. It basically, a Wolf-Rayet star is an extremely bright, extremely high wind, high stellar wind star. And basically, it's blowing off the outer shell as a hydrogen and helium of the atmosphere, and then those same intense winds, stellar winds, are ionizing itself. So basically, it's expelling this. Expelling its atmosphere, and then creating a planetary nebula, and then illuminating it. So next slide here, and that is a James Webb Telescope shot. It's actually one of the, well, they always say it for all these pictures, but it's a James Webb Telescope picture. Next slide. So this is V Sagittae. So it's an eclipsing and cataclysmic variable binary system. It's predicted to nova this century between 2067 and 2099. Most likely it's a white dwarf that's got a companion that it's accreting mass from, and there's been speculation that it might be a contact binary instead. But whatever the case is, the thing is going to light up. It's going to be one of the brightest stars in the sky, somewhere around magnitude 1 or 2. So hang around, goals. Hang around until it blows up. Next slide. And this is an artist's conception that I thought was pretty cool, like casts a shadow on the star. But anyway, that's that. So set your calendar. Next slide. So then there's NGC 6886. This is a planetary nebula. It's probably a, they speculate that it might be a triple star system because of its odd shape. If you go to the next slide here. So last month I was talking about remember the dark doodad nebula I was talking about last month? I was going to name something doodad. I'd be naming this doodad. This seems more like a doodad to me than the other thing. But you've got the polar lobes there, so that shows where your polarity is with your star system. Next slide. So more about Sagitta and its incredibly long list of 7 deep sky objects, which half of which I've covered here, are on these sites. Good sites to look at. More about the Necklace Nebula and what's going on with the physics involving that is at this website right here. Next slide. So this is Sean Paul's Tulip Nebula. Yeah, very, very nice. Yeah, right on. And keep looking up. Thank you.
Thanks, Bill. Next slide. All right, Constantine.
Thank you. Good evening. It's already past 9, so I'll be very brief. As you can see, our total balance is 123,800 something, and that's made up from a number of things: cash reserves, other CDs, and directed donations, leaving us a current operating balance of a little over $8,100. The Rising Star Development Fund is way up at $77,610. And we have a loan payment coming up in October, and hopefully we'll pay it off. I don't want to take any more of your time. If there are no questions, we'll move on. Thank you.
Next slide. There are a couple things we did in the executive board. We formalized the fundraising process, requisition and fundraising process. When we redid the bylaws a couple years ago, we implemented some fundraising stuff. We just haven't addressed all the issues that have come up since then. So we'll be formalizing all this in the bylaws in the fall. But a formal process on requisitioning funds and getting approval process through that. This is just an interim policy until we fix it up. It's next to you right there. Next slide. New cards. Box right here. Got our new business cards if you want to grab a couple. Thanks to Sean Paul for developing this. They look good. And he assures me if I'm looking at Fort Worth at this point, that is exactly how the Milky Way would arise. So yeah, he lined everything up just perfectly. I believe him. Next slide. All right. No infrastructure, legal, business, other business. I don't think we have any other business to talk about. Announcements. Michelle. As you know, we have our annual camp out at Three Rivers Ranch, September 4, 5, and 6. And Michelle is going to, she's going to do the drawing for the cabins.
Oh, that's happening.
Okay, Chris, now, all the information for Three Rivers, I think everybody's aware of it. We're drawing for the cabins tonight. We've had 9 people sign up for it. We've got 6 cabins. So the first 6 that are drawn will get a cabin. The other 3 in order will go on a waiting list. And if one becomes available, we'll contact you and let you know it is. But yeah, there's plenty of room in the bunkhouses. We've still got some RV spaces available. And I think we've got at least one family that's going to be camping out there. And I think right now I've got 33 people who are signed up. So that's good. So anyway, Chris, will you help me draw for the cabins? It's all typed, so you don't have to read my writing.
Mark and Esther Kowalski. Oh, sorry.
Number 2, Robin Pond. Robin's happy. Where's everybody else who's happy for her? And David Ruiz Bello, you got a cabin. Team has not been drawn yet. This is not good. Russ Boat Right. We draw all of them because the last ones will go on a wait list. Folded these real good. Side number 5. Chris Wojnicki, you're number 6. Ted, you're on wait list. You're number 1 on the wait list. Patrick, you're number 2 on the wait list. Patrick McMahon. He's here somewhere. It looks like I'm going to be in the bunkhouse. I'm number 9. All right. Again, if you want the Saturday evening meal, the cost is $20 per person. I can take you tonight, or you can send me a check in the mail. I put that through in the email that went out, and I need that payment by the 31st. And if you want a meal, I need to know by the 31st so that we can let the caterer know. You will not be helping me next year. Thank you, Chris. I appreciate it. Christian.
Thanks, Michelle. That was great. Next slide, please. Oh, I'm sorry.
Is Danny Townsend still here? You want to talk about going out a day early and putting that 30-inch together?
I plan on going out a day early. The 4th, is that on a Thursday or a Friday? Okay, I will be going out on a Thursday, and I've already got one person going out with me. I need probably 2 more. Might have Chris Babin, one of the volunteers, might be able to make it. So maybe 1 or 2 more people that I'll need to help me set that.
You may have to speak up a little more. We can't hear you.
Is it on? Okay.
Thank you.
Yeah, I'm going to need probably 4 people total on Thursday, and we'll be able to set it up probably. So I'll need just whoever can help get with me, and I'll go out Thursday to set it up. Katie told me that the roof was completely done on the 30 observatory. And so we can set it up now.
I might be able to make that, so I'll let you know this week. All right. Thanks, Dan. All right. Anything else on that? Next slide, please. All right, Christian. There you go. Come on up.
All right, I don't know if we have the next slide ready yet, but we want to recognize the people that have done outreach of at least 24 hours. Hello? Can you hear me now? I gotta get close. All right, we want to, as we did last month, we want to thank the volunteers that have put in at least 24 hours of service, of outreach since January 1st. And I think there is yes, this is what the pin looks like. You're going to get a little pin to thank you for your service. Of course, the real thanks is from the people that you help each and every time you go out. Last month, you can see this is our award winners, if you will. These are the people that put in at least 24 hours. And this month, we have 5 more. So we'd like to call each of these people up. Cy, Dave, Dave, Mark, Pam, and Tom. Get a round of applause for them, for their service, and for all the hours that they put in this year. And this is also a reminder to each of you to make sure that when you do come out, to put your time into Night Sky Network. And that is where these hours are pulled from. So record your time. I'm sure there's a lot more people than just this. I see lots of you out there at the outreach events, and thank you all. But these guys get the pin because they put their hours in.
The procedures on how to enter your hours are in the Groups IO, and you count your driving time for that as well. So if you're driving out to do a 1687 event, you're adding about 5 or 6 hours of drive time just to get there. Thank you all. Thanks, Kirsten. Next slide. Patrick.
Okay, so big thank you for people who helped out the previous Star Party, especially Dinosaur Valley. We had about 150 guests, so we had a successful night there. So we have a few coming up. For those who won't be making 3RR, we do have a Star Party in Argyle. Robert Circus will be spearheading that one. Then then on the 11th of September, Watauga has has an annual fishing derby and a family camp out overnight, so we'll be providing some telescopes to view the sky for a few hours. And then the next Dinosaur Valley Star Party is September 12th. Thank you.
Next slide. Ten Hills, John. John's still here? There he is. He's sneaking up on me.
Yeah, I like that. That's a good slide. I want to thank everybody that came out to our Star Party last Saturday night. We had a great one. It was a little on the hot side, so thank you for bearing up and making it through the heat. Our next one is September the 19th. Psychologically, it will be cooler. I can't guarantee that the actual temperature will be or not, but you feel like it's cooling off in September. Anyway, we will have Venus will be fairly low on the horizon. The moon will stick around a little longer than it did on Saturday night, and we'll also have Saturn coming up. And I would like to mention, as I normally do, all the people that are new, that are looking for telescopes, or that have telescopes that they would like to figure out how they work, bring it out there because it's very low key. We're not real red light obsessed like if you're doing astrophotography that you would be, but we're not red light obsessed. So very low key. So just come on out September 19th. Thank you.
Yeah, if you're new, come on out, learn some stuff. Next slide. All right, 1687, next slide. We have 3 events coming up in October. We don't know if it's going to be a Friday or Saturday night yet. We'll figure those out a little closer to the time frame, but we have 3 parties coming up in October. Next slide. Palo Pinto, Michelle.
Just like everybody else who's involved in outreach, we want to thank everybody who's been out to Palo Pinto to help us over the last few months. I can't remember. I think we may have had 6 or 7, 10 scopes. I've got my partner over there. 10 scopes at the last star party we had. And I think we ended up with about 50 to 60 people who came through. The people we're getting out there, not necessarily the campers, we're getting people from Abilene and the Metroplex. One couple was from Plano who came out to the park specifically for the star party. So we're getting a lot of people visiting just for the star party, and they're very intelligent. They ask some very good questions. So it's a good group to work with. And of course, I think as it gets cooler, we're going to end up with more people out there. Our next party is going to be on September the 12th, Saturday. We meet at the main trailhead. It's the state park. It's very easy to get to. Just like with Dino Valley, if you bring your badge, you can show it to the person at the front gate, and your admission is free. Okay?
Thanks, Michelle. All right. Rising Star, this way. Tom?
I've been under the weather for a few weeks, but when I come back from Ohio, I'm going to Ohio, you'll see more stuff coming up. I also wanted to mention, if you guys want a place to go view that's dark within an hour of the Metroplex, I drove out to Palo Pinto the other night and just parked before there's like a turnout before you go into the park, and you can just park there, and it was great. So.
Next slide. Okay, we are looking to change the gate code. I was going to do that last week, but one of the actually the padlock on the 20-foot building would not reset. So rather than reset 5 and not set 1, I'll fix that later this week or next week. I just have to buy a new lock, and we'll do them all at the same time. We also have new directions coming out. It shows you how to line the numbers properly on the gate. You've never done that before. It's a little bit different. Also, instructions on how to sign into the Wi-Fi, and there's a picture map showing you how to get out there, either through Rising Star or Cross Plains. Once we change this, we'll let everybody know we changed the codes. So, next slide. Nothing on the library right now. Next slide. Next slide. George, you on the...
I'm here, sir.
All right, George, it's up to you.
Just wanted to thank Matt for all his media reviews that he's been giving over the years, and just let everybody know that if they have something that they've got as far as a product that they want to review, or just some kind of book that they have been reading that they thought was really nice, please submit, as well as anybody that has pictures of events that they go to. If you'll go ahead and dump that into like a OneDrive or something like that out on the internet and send a link to me, I'll make sure that gets in the newsletter. And then since we've just gone through a deal with everybody re-upping with their dues and such, I'll send out the code to the Astrospheric so that they can get on that. It's a free service for us since we're in a club. They give us a number of slots in there, and we can use them as many as we want. So I'll send that out later on. That's specific to anybody that's into astronomy, and it's geared towards the weather based on that. So other than that, we're good to go.
And what was that again? George, that last thing?
Astrospheric.
Okay. And what does it do?
It's a sky condition app.
There you go. Clouds, wind conditions,
Okay,
moon,
atmospheric condition.
that
Okay,
kind of
thank
thing.
you.
Yeah.
Good stuff. Thanks, George. Next slide. All right.
So next month I've got Dr. Shane Byrne. He's gonna tell us all about the polar caps of Mars. He's actually one of the lead scientists for the HiRISE camera that's at Mars. I think orbiting Mars. I think the HiRISE camera is actually on a couple of different missions. But yeah, that'll be really interesting.
Looks interesting. Next slide. All right, social hour, social house after this. Hope to see some of you there. Next slide. Anybody have anything else we need to talk about tonight? Hearing none, do I hear a motion to adjourn? Motions and a second from Christian. All in favor say aye. Get out of here.